Okay, number 2 on our sample test, we had a region here that was made up from the graph of y equals x cubed, which ultimately we know looks like that. We have a picture drawn for us also. And then 4 times cube root of 4x, which essentially looks like this. So we have that region, and again the two functions in question are x cubed, and then this the function is 4 times the cube root of 4x. Alright, so bottom line here in part A, it's asked us to find the coordinates of the point in the first quadrant where these two curves intersect. And keep in mind this is a calculator problem, so let's not waste any time on algebra. So draw the graph. And do our intersect command. And looks like we get x equals 2. So find the coordinates of the point. Y equals 8. I want the coordinates. 2, 8 is where they meet. Alright, and the next part, part B, they ask us to write an integral expression with respect to x to find the area of that shaded region. So if it's with respect to x, remember we're going to use a vertical slice, so it would be a top minus bottom situation. So we'd go from 0 to 2 of the top function, which is 4 cube root of 4x minus x cubed dx. And with that, again, it is a calculator problem, so we will not spend any time trying to find antiderivatives. So, you are at 9. Oops. Let's see what we get. So we get 4 cube root x minus x cubed. And it's like should be 3.5595, so it'll be 3.560 then.
Oh. Cube root of x instead of 4 cube root 4x.
Oh, you're right. Thank you. Fix that. There we go. So not 3.560, should be in fact be bigger than that, I would expect. Yep. So ultimately 8. Alright. Then they ask us in part C to do the same thing but do it in terms of y, so in other words have a horizontal slice. So if it's a horizontal slice and we want to find the area, we would be going right function minus left function. Now the kicker though, knowing that we're going to go from 0 to 8 also because we're using y coordinates here, so we're going in the y direction 0 to 8. The other part is we need to take these equations and we need to solve them for x. Remember we need to get the x as our independent or dependent variable. So if we solve this, we'd get the cube root of y equals x. That would be first one. So cube root of y equals x if we solve this one. And that is our right function, so we'd have cube root of y here minus something. And ultimately on this one, if we would solve this one for x, we'd have to divide by y. Do that right here. Or divide by 4, that is. So y over 4, cube root of 4x. Cube both sides, so we get y cubed over 64 equals 4x. And then if we divide by 4, we get y cubed. And 64 times 4 would be 256. Be y cubed over 256 dy. And if we have done this correctly, then those two areas that we get should be the same, shouldn't they? So one's in terms of x, one's in terms of y. And one's going right to left, one's going up and down. And bottom line here is if we do our equation, we'll get the cube root x this time minus x cubed over 256. 0 to 8. Provided we did everything right, we hopefully will get 8 again. And we sure do. Questions on either setup? Okay. Last part then asks us to, without using absolute values, write an integral expression that gives the volume of the solid generated by revolving the shaded region about the line x equals -1, and it says do not evaluate. So we want to revolve this around the line x equals -1, which ultimately is over here in our picture. So if we want to take this and revolve it, and keep in mind that we're BC students, so we can use either shells or washers in this case. We can use either one of those slices that I had there. It's pretty much up to you. Bottom line is, even if you were an AB student, you could still use shells. It's okay to use them even though it's not an AB topic, but they still allow for it. I personally would use shells here because these functions are already written in x for us. We know we wrote them in y correctly, but either way, if you're doing shells and we're going, the interval doesn't change. We're going from 0 to 2. And with our general shell method, we have 2 pi. And then remember what goes here is the distance between the shell and the revolving line. And that distance between shell and revolving line is 1 here and x here. So it would be 1 plus x would be the distance between the shell and the revolving line. And then the height is, of course, going to be the top minus the bottom again. So 4 cube root of 4x minus x cubed dx. So that integral will give us correct result. And the other integral, if we want to do it the other way, if we want to do it with washers instead, would have been 0 to 8 this time, pi, and then our outside radius this time, remember, is from here to here, which is going to be 1 plus the right-hand function. So it would be 1 plus the cube root of y squared minus, okay, that's the outside radius. The inside radius is the distance from here to the other function, and that's going to be 1 plus the other, which is y cubed over 256 squared dy. And either one of those would give us the same answer for that volume. And we have a vertical line to revolve it around. So if we use a vertical slice in x, it's going to be a cylindrical shells method because, again, if it's the slice and the revolving line are parallel, it's always going to be shells. If the slice and the revolving line are perpendicular, we're always going to get either discs or washers. Questions on either of those setups? All right. Well, let's go ahead and finish off here with number 3 then. Part of number 3 here already. Number 3, we have a pump that has air in it. It's pumping air into this balloon, and it's actually it says that the pump consists of a cylinder with a radius of 8. Piston moves up and down according to the equation 24 t plus 1 plus ln of t plus 1 over the interval 0 to 100. T is measured in seconds. H is measured in inches. And it says that the piston moves up and down. The total volume of the air enclosed in the pump and the balloon remains constant. And we know that R of t, which is the radius of said balloon, is 0. So in other words, there's no air in the balloon at the beginning time, if you will. Because the balloon would have a radius if there was air in it, which it doesn't. So, bottom line here is that we need to write an expression in terms of H of t and R of t for the total volume of the air enclosed in the pump and the balloon. And so, in general, we know that there's air in the cylinder. We know that the volume of the cylinder is going to be pi r squared h, because it's a cylinder. All right, and we know that the volume of the sphere is 4/3 pi r cubed. And bottom line here is that the H and the R here are variable. They're changing, right? And so if we just use, instead of H, if we use H or T, okay, H is a height and it depends on the time. So that means our final answer then for that part would just be this. It'd be 64 pi. Why 64? Because the radius of that cylinder is fixed. It's just simply 8. Okay? So it would be 8 squared, 64 pi, times H of T. That would give us the volume of the air that's in the cylinder at any given time. And then the 4/3 pi r cubed. Again, the r of T, the r is variable, but we've made it variable by putting in the function r. R represents the radius at a given time. Okay? So if we wanted to know the volume at a certain time, we could plug in the time, and we could do just that. Now in this case, we need a little bit more information if we want to actually find a numerical volume here, because they don't tell us enough to do that quite yet. All right. So bottom line is that would give us an expression for all of the air that's in either both, or that it's in both the balloon and the pump. All right. Now, in part B, it says find the rate of change of the volume of the air enclosed in the pump at time 3. So we know that in general, like I said, that the volume in the pump, the air in the pump, if you will, is shaped as a cylinder, so it's going to be pi r squared h, which we know is 64 pi times h of t, and that is the volume, right, of the air in the pump at any given time. And we want to know what is the rate of change of that volume. So in other words, we want V what? Well, we need V prime, don't we? The rate of change of the volume. So dV dt, V prime, we can think of it either way. Bottom line here is that the derivative of that 64 pi is just a constant. So it would be 64 pi times the derivative of h of t. Okay? And with that, that would give us our volume. And we want that at 3. And so if we did 64 pi times h prime at 3, okay, we'd get negative 251.327 inches cubed per second. And the question is, how come I didn't show any work to get this? It's a calculator problem. It's a derivative at a point, right? Don't spend any time finding the derivative of that h function. Right? It's just a derivative at a point function. Use your math 8. So if you do so, that would be our rate of change of the volume at that point, which ultimately means for us that air is going out of the tank at that point. Out of the tank and into where? It's going out of the tank and into the balloon. Remember, we're not losing any air. Okay? Well, however much air we have at the beginning is still there. Okay? It's just out of the tank and into the balloon. Okay? It's either going out of the tank into the balloon, or it's going out of the balloon back into the tank. Okay? Okay. Now, in the next part, we had, similarly, we want to find the rate of change of the radius of the balloon at time 3. So find the rate of change of the radius. Okay? Now, the radius of the balloon we know is related to V equals 4/3 pi r cubed. All right, because again, we're dealing with the radius of the balloon, which is a sphere. So we know that we're going to be dealing with this equation instead. All right, and ultimately, if we were to want the radius of the balloon, the rate of change of the radius of the balloon, then we ultimately need dr dt. Well, if we differentiate with respect to time here, we can get just that. Typical related rates problem. If we do that work, we're going to get that. And what's nice is that we have our dr dt. True? Right? And that's part of our expression. Now the key is, can we solve this and figure out what dr dt is? Right? So, first question is, let's start with this. What about dv dt? Keep in mind, we want the rate of change of the radius at time 3. What do we know about dv dt at time 3? Didn't we just calculate that? Okay. We calculated it as negative 251. That's because it's coming out of the balloon, or out of the pump, but now it's going into the balloon at that same rate, isn't it? Okay. If it's coming out of the balloon at negative 251, it's going in, or coming out of the pump at negative 251, it's going into the balloon at that same rate. Okay. So ultimately, we know the dv dt is 251.327. And then we have 4 pi, and then I left that blank because, again, dr dt is what we want. What about the radius of the balloon? Got to think about that one. How are we going to find the radius of the balloon at time 3? keep this in mind. What is the radius related to in this problem? The radius of the balloon is related to the what? What is the radius of the balloon related to? What shape is the balloon? It's a sphere, so it's related to the volume of the balloon, true? So if we knew the volume of the balloon at time 3, we could figure out the radius, couldn't we? And then in turn use that in our equation here. So the question is, how are we going to do that? How are we going to figure out the radius, or the volume of the balloon at time 3? Well, let's think about this. Remember, one of the key information here is that this air, the amount of air, doesn't change, right? So if we knew how much air was out of the pump, wouldn't that tell us how much air was into the balloon at that same time? Okay. So ultimately, if we could find V of 3 for the pump, okay, then we would know how much air we have at V of 3, and if we knew V of 0, then subtracting those two would be how much has gone out of the balloon in that time frame, wouldn't it? And how much has gone out of the pump is going to be how much is in the balloon. And so if we knew that, then we could figure out the radius in question. So let's figure that out. What about V of 0? Okay, remember, keep in mind that we know that our V here at any time is this. Okay. So it's 64 pi h of t, that's our volume in the pump. And so h at 0, if you put a 0 into that equation, you get 24 over 1 plus ln 1. ln 1 we know is 0. So that would simply be 64 pi times 24. I'm going to leave it unsimplified for the time being. And then if we do V of 3, we got 64 pi times h of 3. And if we put a 3 in there, we're going to get 64 pi 24 over 4 plus ln of 4. Alright. And so that right there would give us our volume at time 3. So let's go ahead and calculate that change in volume from time 0 to time 3. Again, it's a calculator problem, so if we do 64 pi times 24, so that right there is how much we had in at the beginning. That's how much air was in this whole system, actually. Because remember, all the air is in the pump at the beginning because the radius of the balloon is 0. So that's how much air is in the system at the beginning. And then we're going to subtract from that, okay, how much air we have at time 3, which is going to be 64 pi times 6 plus ln 4. Alright, so ultimately that's our change. So for this particular problem, remember that number right there, 383717, okay, that's how much air went out of the pump. But for us, that's how much air went into the balloon. True? So if we know that that is our amount of air that is in the balloon at this time, if we solved this sentence right here, that would give us our radius at that given time, wouldn't it? Alright, so let's take that number and we'll divide it by pi, and we'll multiply by 3/4 to get rid of the 4/3 in the pi, and then we'll take the cube root. So our radius here turns out to be 9.7 or 2733, etc. And remember, where does that go? That's going to go right in here. So if we're going to solve for dr dt up there in that previous equation once we found that key radius, and we're going to square it, we know. So if we square that number and we multiply by 4 pi, and then we divide that into 251.3271, we'll get our dr dt, which is 0.233. And if we solve that sentence, that's what we did to get to 0.233. And dr dt, r is measured in inches, and our time is measured in what? Did they tell us? Oh, there it is, seconds. Inches per second. So 0.233 inches per second. Slide it down a little bit. Alright, so that was a good related rates problem because we had to kind of think carefully how are we going to find that radius. And again, the key issue is that the air in the system doesn't change. Okay, however much air is in at the beginning is always in that system. The air, there's no leaks at all, so how much air is in that gets pumped out of the tank is the same as what got pumped into the balloon. Okay. All right. How about the maximum volume of the balloon when it occurs? I handled it as such. If there's a maximum amount of air in the balloon, then there would be a minimum amount in the tank, wouldn't there? Wouldn't that be true? So I handled it that way since we have a nicer equation for the volume of the air in the tank. Since the volume we know is that 64H of T. So if we want to minimize the volume here, we find its derivative, which we know is that. So if I found the derivative of that, and then I set that equal to 0. And of course I spent absolutely no time trying to solve that by hand. I just got the answer with my calculator, got 23 seconds. Now, one of the things that we had to think about here is that the actual answer to the question, though, the when it occurs part is that's 23. That's the correct answer there. That's the minimum for the tank, which would be the maximum for the balloon. Okay. But the bottom line is when I did my equation, and I don't think I still have it in there, but I'm minimizing that, so I'm getting how much air is in the tank. Right. When my y value. Okay, but that's not the answer though, because we don't know how much is in the balloon. So ultimately, what I got for my y value, I just subtracted from that 4,800 number. Remember, there's 4,800 total, and if there's 800 in the tank, then how much is in the balloon? 4,825 minus the 804, 840. So bottom line is, again, we had this was our amount in the whole system, right? And there was this much in the tank. Okay? So therefore, what am I going to do with these two? Actually, I don't want that there either. So this is how much was in the tank at that time. All I got to do is take those two and subtract them. And if I subtract them, I get 3,900 and something. I don't remember off the top of my head. I think it's 3985.439. Which is cubed. All right. So like I said, that was the only drawback with doing the minimum in the tank. Was that you had to recognize that the y value wasn't the right answer here. The y value is how much is in the tank, so you just need to subtract that from the total to get how much is in the balloon part. Okay, and there's your answer for the balloon part. Okay, so for Monday, make sure you got your 4 through 6 done from 2008, and then we'll carry on with 4 through 6 in this packet next.